Hello students, in my last YouTube interaction with you, I had introduced statistical thermodynamics. I told you how it is important and it acts as a bridge between quantum mechanics and classical mechanics so that you can chart out the entire evolution of the properties of a material starting from its atomic state, from one atom to a bulk phase where you have millions of atoms, maybe millions and millions, zillions of atoms would be there. So that is the importance of statistical mechanics. It helps you connect the individual property of an atom, and when there are many atoms together present in a container or in a solid crystal. So I also told you that in analogy to quantum mechanics, it is partition function is a term that you will encounter more often, and it is a very important term in the sense that it contains all the information about the properties of the matter. So that's a thing that we need to understand, and we will focus on that. And the observables are all related to this partition functions. All the properties that we talk about will be related to this. So we are going to focus more on the partition function. I also told you last time how to write a partition function for a molecule which behaves as a rigid rotor, and I also told you how to write a partition function for a molecule assuming it to be a simple harmonic oscillator. So these are things that we covered last time. I also talked about the significance of these things. So the number of states that are thermally accessible, that is what it is reflected in a molecular partition function. So as at t is equal to 0, ground state, only the ground state is accessible. At very high temperatures, virtually all states are accessible. So this was the thing that we had concluded last time. So this was the situation for harmonic oscillator. We also learned how to write the partition function for simple harmonic oscillator, as you can see here, and you can also see we discussed all the distribution profiles that we see in this slide. So when the temperature is very, very low, tending towards 0, you can see that only the ground state is populated. There is only very small population over here, and as you raise the temperature, as the temperature is increased, the population gradually gets distributed over these higher excited states. So if you go on increasing the temperature, gradually you can see the population has decreased here, but still in all these cases you will find that there is towards the lower energy side there is greater population, and as you rise upwards the population decreases. So this is what is the essence of a partition function is. It tells you how a set of molecules are distributed over different energy levels, or in other words we can say that how they are partitioned in over a given set of energy levels at a given temperature. So that is what a partition function tells you, very important thing. So this is how we relate this this is the idea of partition function, and as we move ahead, we will talk about real systems. So this was a system we had discussed simple harmonic oscillator considering only the vibrational motion, which was a model for vibrational motion. Similarly, we considered rigid rotor, which was a model for rotational motion. Now in a molecule, when we go to a molecule, we have all these motions are taking place simultaneously. So we have translational motion, rotational motion, vibrational motion. So all these energies will contribute to the total energy of the system. So we will, when we write partition function for a molecule, we have to take the contributions from each one of them. So that's what is, we start with this expression first. The energy of a molecule is the sum of contributions from different modes of motion. Modes of motion: translational, rotational, vibrational, and they are initially in the ith state, energy state, and so on. So this is the meaning of the terms that is given over here. The electronic contribution, this needs to be clarified that electronic contribution is not a mode of motion. All these three are modes of motion: vibrational, rotation, and translational. But electronic contribution is not a mode of motion, but it is important because it contributes to the energy of the molecule, and so we have included it over here. The separation of terms is what we are seeing here, is that these terms are separate. We are writing it separately in additive way. So this tells us that they are independent of each other. Translational motion is independent of rotational, rotational is vibrational, and so on. So each one of them are independent of each other. That is an approximation we have taken. However, we will see later on in many cases that it is not entirely independent of each other, but it works very well. If you just work it out this way, you are very closer to a real picture of a molecule, how it behaves. So we will stick to this. In this class we will be learning only this part, assuming that these different modes of motion do not intervene into each other, they do not depend on each other. Okay, so the separation of electronic and vibrational motion, so this is actually based on the Born-Oppenheimer approximation. We understand that electronic ground state, if we are considering about only the electronic ground state, the vibrational, the separation of vibrational motion and electronic motion is justified, these two. But if we consider an excited state of electronic state, then these two are correlated. So let's not go into that complicated system at this moment. So we are considering electronic ground state, and then vibrational, rotational, and other things. Within that electronic ground state, we will be discussing different states of vibration, rotation, and translation. So so this is what we have. So we have found that it is sum of independent contributions. The partition function can be then factorized in this way. You can write is that individual sum of all the partition functions, all states. So you if this is the energy epsilon I, beta is the 1 by kT, that we have already discussed last time. So in this context, it can be written as factorized into translational, rotation, vibrational, and electronic functions in this manner. So you can expand it further. So instead of all states, you can write translational, rotational, and accordingly you can separate the terms. You can separate the terms in this manner, taking the summation, and for each of these summation in the brackets we can write qt, that is the partition function for translational motion, partition function for rotational motion, partition function for vibrational, and partition function for electronic state. So these factorization help you in understanding the bulk property. Eventually it will help you in understanding the connection between the individual property of then a molecule, an atom, and the bulk property of a system. So this is why it is important. So at a glance we can see what they look like. the expressions, for translation, rotation, and vibration, electronic. So the expression of partition functions will look like in this manner: V by, this is lambda, capital lambda. It looks a mirror image of V, but it's pronounced as lambda. This is capital lambda, and it has an expression like this. We'll see how we get it. Then rotational, in case of rotation partition function, kt by sigma hcb bar, or it can be simplified as this, t by sigma theta r. Similarly, for the non-linear molecules, it gets slightly complicated, but this is the expression. But in this class, we will be focusing only on the linear molecules. Then vibrational part will look like this, and we will see that for electronic state G naught, the ground state plus the higher degeneracy of the ground state plus higher energy terms will come into the picture. So we start with this, the translation partition function. For deriving the translation contribution, we assume it to be, as we said, we start with the model. You have the ideal model of a particle in a box. If you start from there, considering the x as the length of the vessel, length of the container in which the particle is. So in that case, you can assume that L, the length, is equal to x, considering only one dimension. So your energy of the system can be given by this, as we have derived in case of particle for a one-dimensional box, particle in a one-dimensional box. So this energy is relative to the so lowest energy level will be n is equal to 1, and so we can write this, the energies relative to this level, as if we express this as epsilon, then epsilon n will be n square minus 1 into this. So this is how we where epsilon is h square h by x. So keeping this, if you substitute n is equal to 1, you get h square by 8mx square, and in relation to this you can define all the energies. So relative energy, so with respect to the ground state energy, we define all the energies as we have been doing in earlier in the last class. That's the basic thing that we do in statistical mechanics. We take the lowest energy as 0. So that's the thing that we are doing over here. The sum to evaluate therefore is this. You take n square, so this is the expression. We simply take this expression, multiply it by beta, and evaluate the partition function. So this is the partition function to be evaluated. So we assume that this is the translation energy levels are so close to each other. The energy levels, if we analyze in a container, if a vessel is large enough as compared to the particle, if it is very, very large, the energy levels will be very close, so close that it will look like a very continuum kind of thing. So then in that case we can use, instead of summation, we can replace this summation with integral sign and evaluate it within the limits from 1 to infinity. So this gives you n square minus beta e, which can be the extension of the lower limit to n is equal to 0. You can see here we are changing it to 0, and the replacement of n square minus 1 by n square introduces. So this is done in accordance with the principle of statistical mechanics that we initially discussed in the last class. The first state you have to take as 0, lowest limit replacement of, and the replacement of n square minus 1 by n square. So when to simplify the equation, we are trying to simplify this equation here. So there is negligible error when we replace this term n square minus 1 with n square. but it will help us in understanding better, because it makes a simpler equation without affecting the results much. We make the substitution. In that case, we substitute. Then x square is defined as n square beta e. This whole term is defined at beta epsilon n square beta t. This is taken as x square, and dn is taken as dx by beta e. So we write the entire equation in another form in terms of x in this manner. This is the constant term, and this e to the power minus x square dx. So this is a simpler way of writing the same equation. And so if you integrate it within the limits, this is the value that you will get, under root pi by 2. So the entire thing gives you, in the final analysis you will get 2 pi m by h square beta, this whole under root into x. So this is the expressions for partition function in for translation motion in x direction. But a molecule may be moving in all the 3 dimensions, x, y, z. As we know, it is in random motion. So we have to consider all these things, and okay, so we will extend it to in all the 3 dimensions later, in just a moment. But here there is an important point that I would like to highlight, that here there is the expression can be, we are further trying to simplify this expression. So we have x, and this whole term actually has an because partition function is a dimensionless quantity, so this is also having this factor is found to be having the dimensions of a length. So x by lambda, this is replaced by a term which we call it as capital lambda. This is called thermal wavelength. So x distance by wavelength, so both has the same dimensions. So that's how we get it. It is a dimensionless, in the dimensionless form, overall function. So this is uppercase lambda that we talked about. This is similar to the de Broglie wavelength, thermal wavelength. We call it thermal de Broglie wavelength, or simply the thermal wavelength of the molecule. Then so now you can simple relation, you can see it has an inverse relationship with partition function. So as the wavelength increases, the partition function will decrease. And thermal wavelength, how it is increases and decreases with mass, that you can see. If the mass increases, thermal wavelength will decrease. If temperature increases, then also thermal wavelength will decrease. So this is the thing that we understand from here. So x by lambda, capital X by capital lambda, where lambda has this kind, this is the expression of lambda here. This expression shows that partition function for translation motion increases with length of the box and the mass of the particle. So if you increase the mass of the particle, lambda decreases, and this partition function will increase. Or if the length of the box is increased, it should increase also. So which means the separation of energy levels becomes smaller, and more and more levels become thermally accessible. Okay, so that's what it means when we say that partition function increases. That means you are talking about more and more energy levels being made accessible at a given temperature. For given mass and length of the box, the partition function also increases with increasing temperature. So we just discussed that part also. The total energy of a molecule free to move in 3 dimensions is the sum of. So now we come to this part. As I was telling you, a molecule may be moving in all 3 dimensions. So we have to consider the energy as a summation. Translation energy will be a sum of all these components: energy due to translation motion in x direction, y direction, and energy due to translation motion in z direction. So if you do that, take the summation and utilize this formula for simplifying the mathematics. E to the power a plus b plus c can be written in this form. So if we are writing it x, y, z as this summation here, it can be simplified in this manner. We can go on writing this e to the power minus c. So exponential to this e to the power minus beta e epsilon n1, e to the power minus beta e epsilon n2 along y, along z n3, and so on. So this is so we get three components here. Clearly you can see summation, and these three are so partition function, translational partition function along x, translational partition function along y, translational partition function along z. So these are three things, components that we have got. So these equations is typically for x direction. The only so what we do here is that we simply multiply y, z over here, and we get an expression like this for particular molecule moving in all the three directions. And because this x, y, z, if length along x, y, and z is multiplied, we get the volume. So we can replace this x, y, z term with v, and v by this capital lambda cube. So you remember translation partition function, the denominator and numerator look like a mirror image of each other, with the difference that it has this is a power raised to power 3. So v by lambda cube, that's the partition function for translational motion. Okay, so now you can correlate with the same as in the one-dimensional case. We have, if mass increases, you have if mass increases, you have there will be an increase in the partition function, and if temperature increases, there will be there will be again increase in the partition function. So as in one-dimensional case, here also when you increase the temperature, go on increasing the temperature, if it temperature approaches infinity, the partition function also increases to infinity. So we can say that the number of states that's now accessible at such high temperature is infinite. So so this is one example where you have been shown, it is shown that how you can calculate the translational partition function. So for hydrogen molecule, if you are asked to calculate, given these other things here, 100 ml vessel at 25 degrees C with a mass of H2 molecule as given over here, 2.016 AMU. So simple, you put the formula first, evaluate this lambda, that is the thermal wavelength. So it can be easily done, substituting the values for H and 2 pi m as we have done. So converting into so keeping in mind the units that we are using, and so the thermal wavelength or the thermal de Broglie wavelength for H2 molecule is found to be this, and the partition function can then be evaluated as this. So you can try calculating the partition function for D2 molecule, simply doubling this factor mass. How you are going to do it, you can just work out. So so one more thing that we have to take into keep in our mind, that we have said, as at the very outset I said, that it is an approximation. There might be some cases where this may break down, this may not be valid, the equation may not be applicable. So what is here, because Q is the total number of accessible states, average number of states per molecule is given by Q by N. And so for this to be acceptable, the Q to be acceptable, we must have that V by NA lambda cube in the denominator this term must be much greater than 1. So if the total volume divided by number of particles, this gives you the volume of a single particle. So if you try to find out, if you just think over it, you will see that this is actually, we are talking, if we do it this way, we can find out the separation between the particles d, which will be the V by N within brackets raised to the power 1 by 3. So this is this gives us the separation volume V by N and in this manner. So the condition we have to feel, so what we see that the condition actually emerges is that the separation between the particles have to be much larger than the capital lambda, that is the thermal wavelength of the molecule. So this is an essential condition that must be met. So in this case, so in most of the cases you will find actually that this is applicable, but in a few cases, if there are few exceptions there where it might not, the equation that we have derived is not valid. For example, consider S2 molecule, 1 bar 298 Kelvin under these conditions. The average separation D turns out to be 3 nanometers, which is significantly larger than thermal wavelength 71.2 picometer. But consider the same, so this is the case that we are talking about hydrogen molecule in a container, normal container. If you put it in a vessel in a laboratory, this is the kind of situation. You will have the average separation would be around 3 nanometer under these conditions, which is much larger and in comparison to the thermal wavelength. So you are satisfying this condition and you can use this equation. But if you consider the same hydrogen molecules within the pores of zeolites or clathrates, then the size of these pores in the zeolite and clathrates is almost comparable. It is comparable to the size of to the thermal wavelength of the hydrogen atom, and in that case the thing that we assume, they are not, the separation is not much larger than the thermal wavelength. In that case it is difficult, this equation may not be valid. So partition function for non-symmetric, so now we come to this part of rotational contribution. We try to evaluate this part, and as we did in the case of rigid rotor, we had derived this equation for molecule of AB type molecule, linear, obviously it will be linear if it is diatomic. So we try to substitute some of these values, and then a few more points will come up. At room temperature we will have Kt, so beta is around this value at room temperature, 200 cm inverse. So the rotational constant of most of the molecules is close to 1 cm inverse. So what does this mean? This means that most of the rotational states will be populated at room temperature, because Kt by Hc term is much higher as compared to this. But if the separation between energy levels, so this is the case, normally this is what the case is, the separation between energy levels is very less as compared to the kT term, this beta term. On the other hand, if you, so this beta bar, B bar that we have, this is the rotational constant that we are talking about. So this rotational constant has a value of 1 cm inverse, but in very light molecules such as hydrogen, this has a much higher value, around 60.9. That is, so this is an exception, and under these conditions, the separation between the energy levels would be much greater, and most of this at room temperature, with the only the ground state is mostly populated. So for linear rotors, the partition function turns out to be kT by hc b bar. B is the rotational constant expressed in terms of cm inverse, and this is the expression for non-linear rotors, but in this class I will focus on linear rotors. This is the simplest case scenario which we must understand fully, only then we should move to the non-linear part. So in case of a nonlinear rotors, instead of you have A, B, C as the three different expressions for rotational constants corresponding to the three different modes of rotations. So when many rotational states are occupied and kT is much larger, so this is the essence that I was trying. You have kT, if kT term is much larger than the separation between energy levels, so that is the situation in most of the molecules. But if you are talking about hydrogen atom at room temperature, the kT term is much smaller as compared to the separation, and all the states may not be populated. So most of the states, so normally, so what I am saying it again clearly, normally many rotational states are populated for given molecule at room temperature. Only in some exceptional cases where the molecule is much lighter, it has mass is very less. In those cases, the separation between the energy levels will be more, and the population in the first excited state and higher excited state will be much lower as compared to the ground state rotational state. So this is the partition function that we write for rigid rotor. The integral, so we again try to simplify it, write it form of x. So we define this as x in terms of x, e to the power x, and as this. So dx by dj becomes beta hc by b bar 2j plus 1, and therefore we have dx. So this becomes like this, and so now we can again simplify it in this manner. So we get a simple expression e to the power minus x dx, evaluate it within the limits to get the molecule. So this gives, when you do this, qr will turn out to be, so this is how we derive this expression for linear rotors. This is how we derive it. And you must be sure of, you must know what this term B bar is. This is the rotational constant that we are talking again and again. Normally we do express the energy levels of rotational rotation motion in this manner with a quantum number j, and the separation is represented in terms of 2b, 6b, like this. It comes out to be like this because the energy expression of energy is this, j into j plus 1 into b, where the b is nothing but h cross square by 2i. So this is important. This is b, our proper rotational constant expressed in joules. The I is the moment of inertia, which is mu r square. Mu can, so for a system of a mass m1 m2 as a diatomic molecule we are talking about AB type, this will be the case. And the B bar, remember the B bar that we are talking about, we are only trying to get it in terms of Cm inverse. What was coming out to be in terms of energy, it's in terms of joules. We are expressing this B, the B over here is expressed as Cm inverse, and to do that we simply divide it by c, the speed of light. So this B bar is simply this term that we are talking about again and again, because spectroscopy of rotational spectroscopy, vibrational spectroscopy, the scale is expressed, axis is expressed in terms of Cm inverse. So we are expressing, to get it into a spectroscopic terminology, we express it in this way and give a bar over it. So a useful way of expressing the term is that expressing temperature above which the rotational approximation is valid. So we have clearly found that there is a temperature above which this expression that we have derived would be valid. Below that temperature it may not be valid. So the temperature above which the approximation is valid is said to be rotational temperature, which is Hc beta by k, or in other words, so at high temperatures, as T is if the T is much larger than theta r, under these conditions the rotational partition function of a linear is simply T theta by r. So this is theta r is expressed over here. You can see here hydrogen molecule, very high value of theta. So it only above this temperature our expression, the mathematical expression is valid. For HCl it is much lower. You can see that as we are gradually moving to heavier molecules which has greater mass, this theta, the temperature at which the rotational temperature is decreasing, and you can see that for CO2 and iodine almost all the temperature above 0 is valid. We are 0.053, so above this temperature, this is we are very, so almost all the values of temperature, so all the values of temperature, it will, at all the values of temperature it will act as the expression, that the partition function expression will be valid for these molecules. But in case of hydrogen, up to 88 Kelvin we cannot apply that equation. Okay, so this is one important conclusion that comes out. And then a higher temperature means T is much greater than theta r, and under these conditions the rotational partition function of a linear molecule is can be expressed in these terms, T theta by r. So you can see in each of the cases, whether it was translational partition function or rotational function, we are trying to get a simplest form, get the expression into simplest form. There it was length by length, here it is we are expressing that in temperature by temperature, some type of, so that is the kind of, so there it was like you had length x by divided by thermal wavelength, so that dimensionless quantity you were getting. Here also you are getting dimensionless quantity in other way, in a form of temperature by temperature terms. So so theta r is shown over here. We just discussed this part. So H2 is abnormally high. The temperature, the rotational temperature for H2 is abnormally high, and above that temperature the approximation is valid. So a general conclusion at this stage is that molecules with larger moments of inertia have larger rotational partition function. So we have seen the relation between as the moment of inertia, and the rotational constant and the partition function. All these three are correlated, as we saw in this. Here is the expression for rotational constant in terms of joule, rotational constant in terms of Cm inverse, and this is related to energy in this way. Okay, so this is the expression that we get. So it is not difficult to understand this point, that molecules with large moments of inertia will have a very low value of rotational constants, and so partition function will accordingly can be evaluated. So so the temperature, so you have a large range of temperature over which This will be valid for larger molecules. So the larger value of rotational partition function reflects the closeness in energy. So a large yes, so that means the separation as we discussed earlier. We have seen here that if B is large, this separation is large. If B is small, this separation is small. So whatever factor, when you have a large molecule with mu r square, mu becoming very large, then this separation becomes very small. So that is the point which we talk about over here, that it talks large value of partition function reflects the closeness in energy compared with Kt, and rotational levels. So rotational levels in large heavy molecules and the large number it means that in case of a large molecule, most of the a large number of rotational energy levels would be accessible. A molecule population of molecule will be distributed amongst different a variety different numbers of rotational energy states. In case of hydrogen molecule, it will be all the population will be along the ground state at a lower if we are normal temperature that we talk about. Okay. So that is the important point that we are trying to point. That we are discussing here. Homonuclear diatomic molecule are all symmetrical. Homonuclear, that is both the atoms are same. If you have a diatomic molecule is like that, in that case. So rotation, so when you rotate a CO2 molecule, one rotation by 180, another rotation by 180, so within a 360-degree rotation you are getting two equivalent structures that you are getting. So a 180-degree rotation results in indistinguishable state of molecule, or you can say that equivalent configuration of the molecule. It brings about a rotation by 180 brings about equivalent configuration of the molecule, which is you can't distinguish between the two. So the number of thermally accessible states is will be only half of that number that can be occupied by a heteronuclear diatomic molecule. So if you have AB type molecule or A2 B2 type molecule, there is a difference. In case of AB type molecule, that is heteronuclear diatomic molecules, when you rotate it by 180, you do not get equivalent configuration. During entire 360-degree rotation, you only get there is only one distinguishable configuration you are getting, that is the original one. So we define here, so in case of so such molecules which linear molecules with which are such as all homonuclear diatomic molecules, or molecules like CO2 or ethine, each one of which on rotation gives two equivalent configurations within 360 rotation. So we divide it by 2. The partition function is divided by 2. So T theta 2 theta r is the expression that we get in simplified form. So this 2 that we are dividing over here is called symmetry number. Symmetry number, which is simply the number of indistinguishable orientation of the molecule during the rotation. So we denote, in that case we can simplify and write the modified equation as this by introducing this term sigma. It's the symmetry number T theta by r, and this is additional sigma term, that is symmetry number that we are considering. For so this sigma, the value of sigma for a heteronuclear diatomic molecule is equal to 1. For homonuclear molecules, it will be an other symmetrical molecule such as CO2 having a center of symmetry. ethylene having ethine having center of symmetry, sigma this sigma will be 2. And similarly you can extend it to other molecules like ammonia, methane or benzene, and then you will find that the symmetry number is 2 for water, 3 for ammonia, 12 for CH4, that is methane, and 12 for benzene. So because you have already studied group theory in your first semester, you should be able to find out this equivalent configuration that is mentioned over here. It is not difficult to understand. In case of water, you have a C2 axis and a rotation, a 180-degree rotation interchanges the position of the two hydrogen atoms, and both are equivalent. So you are having two equivalent configurations within one rotation, one complete rotation. In NH3 there are three indistinguishable orientations. In a similar fashion, if you analyze the NH3 molecule, so A, B, C, if you can move by 120 degrees each time, so in the entire 360-degree rotation you are coming across three equivalent configurations. So the symmetry number is 3. In case of methane, you have in case of methane CH4, any of the three 120 rotation about one of its 4 axes, CH bond axis, leaves a molecule in gives a this is equivalent configuration. So this is something that you have already studied in your group theory classes. Please go through and revise that part. So symmetry number will be there are 4 CH bonds, so and each one of them gives 3 configurations which are equivalent. So 3 into 4 total will be 12 equivalent configurations. Similarly, you can analyze benzene. Any of a 6 orientation around the axis perpendicular to the plane leaves it unchanged. So what we are talking about is how we get the 12 configurations. You simply see, if you have a axis over here, the C6 axis at this point, which is coming out of this plane of this screen, so that's perpendicular to the screen, then you rotate it by 60 degree. So A, B, C, D, E, F, you can perform 6 rotations, 1, 2, 3, 4, 5, 6. You can get 6 configurations which are equivalent, and you have 6 C2 axis also in the plane of the molecule. So 3 of which pass through the atoms B, E, A, D, C, F. So these two will also so each one of them will give you 2 configurations, 3 axes, and you also have axes which are not going over, which are bisecting these bonds, AB bond, DE bond. You have so you can draw a line from here to here. So that is another type of C2 axis. So each one of them, so 3 C2 axes passing through the atoms, 3 C2 axes passing through, passing in between the atoms. All of these giving, so 3 into 2, you will have, you are getting 1, 2, 3, 4, 5, 6. So total you will get 6. So in this manner, if you perform the rotations, you will get overall 6 different configurations, 6 equivalent configuration again. So 6 plus 6 is 12. That's what we get over here. So this is in a similar fashion. We can also discuss the vibrational contribution. Vibrational contribution can be, it is based on the consideration that we have already discussed in case of simple harmonic oscillator. So the expression, so in this case, but what we have to take into account that the number of vibrational motion, the modes of vibration could be very large. So we have to sum up over all the modes of normal modes of vibration. This partition function has to be summed up accordingly. a polyatomic molecule, each mode, normal mode, has its own partition function. We assume it to be harmonic oscillator and then work out this thing. So that's what we are assuming here, that anharmonicity is very low, and each of these modes are independent of each other. So for different modes of vibrational, like stretching vibration, bending vibration, we have to so we assign 1, 2, 3, 4 like this, and we evaluate the partition function in this manner, and total partition function will be summation in this manner, multiplied as this, as you can see, individual contribution are multiplied to get a final contribution, final value, which represents the overall vibrational partition function. So the vibrational excitation is, if the vibrational excitation is not too great, the harmonic approximation may be made, and vibrational energy levels are written as this. So here this V mu bar is the wave number again. In terms of, we are expressing this thing in Cm inverse. So different stretching frequency, bending frequency are different in a molecule. Within a molecule, different vibrational modes have different frequencies, so that's how they are correlated. And so it is basically derived from the simple harmonic oscillator equation, energy expression of energy of the simple harmonic oscillator. And so that's how we write. And if this is the expression. So you substitute this value of beta epsilon, and you will get expression like this. So for given vibrational mode mu, you will have, this is the kind of expression you will get. You will sum it over, and as done previously in case of simple harmonic oscillator, we converted it into 1 by x, 1 by 1 minus x kind of thing. So that you can understand. You can see this. So this is what you have already done in your simple harmonic oscillator case, and we simply move ahead with this, and we try to understand the partition function. Somehow this is, so this expression is clear. I think you are able to grasp the concepts. Excuse me, there's a problem with the computer, I think. It's not, just a moment. So this was the expression, and now that this is the expression that we will get in simple case. And now if I so we have simply substituted the we have the expression of partition function for simple harmonic oscillator. We substitute this value for a molecule based on simple harmonic oscillator, the vibrational frequency and all this. So we can have this kind of expression which can be simplified. You just go back and look at how we have done this in the simple harmonic oscillator. It is detailed in my previous lecture. So if you do that, okay, so this is the expression. Now if you plot it against kT, this is the kind of expression you will get. This is the graph you will get in case of polyatomic molecule. You choose one mode and then you can plot. So for diatomic molecule, there is only one mode of that is symmetric stretching mode, and this is the kind of function that you will get. And for a polyatomic molecule, each of the mode will give you this kind of graph. So this is the vibrational partition function of a molecule in the harmonic approximation. So if you are talking about a very high temperature, at very high temperature, the partition function is almost linear. It is linear, in fact. From here onwards, you can see that it is going linear from at higher temperature when T is much greater than the for temperature at which T is much greater than the vibration temperature. You will have a straight line like this. So in many molecules, the vibrational wave numbers are so great, such as again in case of lighter molecules, smaller molecules, lighter molecules, the stretching frequency is high, CH4. So why it will be so? You must know that now. How the mu is related, frequency is related to the mass and bond strength that we have already discussed in quantum mechanics. So you know that. So in case of molecules, this is so large. In case of CH4, it is so high that at room temperature, this term beta Hc mu bar 6.3 is equal to at room temperature. So most CH stretches normally lie in the range of so we have a CH. So because of this, we have this CH stretching frequencies are very highly energetic. They lie at higher wave numbers, and this value is large. So exponential term that we in the denominator, QV is very close to 0 in that case, which means essentially, what does this mean? That if it is close to 0 exponential, that means the vibrational partition function for a single mode is very close to 1. So Q is very close to 1, which means that only the ground state is mostly occupied. So whenever you have large separation between the energy levels, it is the ground state only which will be occupied, because kT is small as compared to the separation between the energy levels. So if you consider the bonds with low vibrational frequencies, such so this is we are discussing two cases which are in contrast to each other. In one case, the beta Hc mu bar term is was greater than 1 over here, and in the second case it is much less than. There's molecules in which the separations between the energy levels will be very small, vibrational frequencies will be small. So in that case, the expression would be partition function may be approximated by the series e to the power x, and it can be evaluated using this equation. So this term, so weak bonds at high temperatures, this can be further simplified. This equation gets simplified further. You have only this term remaining. The higher order terms are neglected, and you have beta Hc. You can beta is 1 by kT. So kT, if you can express in this way, kT by Hc mu bar. The temperature for which equation is valid is now expressed as this. This is called vibrational temperature, theta V. The theta V. So again we are trying to simplify the equation to get it as simple form as possible. So we are finding a temperature under which the equation, the approximation that we apply will be valid. So this theta V defines the temperature. So a previous table that we discussed, we had shown the vibrational temperatures also. So again, the hydrogen will behave abnormally. It was behaving there also abnormally because we have very light atoms. The molecule is very light, vibrational frequency is high, and so the approximation that we were trying to implement may not be valid. In terms of vibrational temperature, high temperature means T is greater than, much greater than theta V, and when this condition is satisfied, you have QV will be equal to T by theta V. So this is similar to what the expression we had got in case of rotational partition function. We had T by theta R, that was here we have T by theta V, that is T by rotational temperature, T by vibrational temperature. It is as simple as that. And you remember how to get what is the expression for theta V, Hc mu, Hc into frequency by K. So H is constant, C is constant, K is constant, only mu. So Hc by K into mu bar, so frequency into Hc by K. So this is how you can remember this thing. Then we have electronic partition function. Electronic energy separations from the much higher as compared to vibrational levels, vibrational or rotational energy levels. And so here mostly at a normal room temperature you have only the ground state would be populated, and QE partition function is expected to be 1. An important exception arises in the case of atoms and molecules having electronically degenerate ground states, in which so in most of the molecules you are going to get at room temperature QE, the electronic partition function will be equal to 1, meaning that only the ground state is significantly populated. Only the ground state is 100% populated. The situation is different when the ground state itself is degenerate, electronically degenerate, in which case the partition function will be equal to the degeneracy of the system that we are talking about. Such an example we have in case of NO molecule, nitric oxide. Alkali metal atoms, in case of alkali metal atoms also you have example double degenerate ground states we have because of the orientation of the electron spin. So in that case also you have because QE is equal to 2 degeneracy, there are two ways in which the electron spins can be arranged. Some atoms and molecules have low-lying electronically excited states at high enough temperatures. Low-lying electronically excited states. So in those cases also, we will discuss this case also here. So an example of this case is the NO molecule, in which case, in which the configuration, molecular electronic configuration can be written as pi to the power 1. This is the only the topmost valence orbital that we are showing. The orbital angular momentum may take, so there is unpaired electron. This is a molecule which has unpaired electron in the pi molecular orbital. The orbital angular momentum may take two orientation with respect to the molecular axis. So you have the molecular axis, and there can be two values of spin angular momentum corresponding to that. The spin angular momentum may also take two, so spin angular momentum can have two different orientations. Orbital angular momentum will also can have two different values, so orientations. So the degeneracy is total degeneracy that you will calculate will be 4. So this is the situation that we have. This is the ground state, degenerate ground state, 2 pi half, and in this in the ground state you can have two situations, two ways in which the spins will be oriented. The spin could be in this manner, and the angular momentum, capital L, this blue line is anti-parallel to this. So the spin can be down spin can be up spin. So accordingly, if you put the L, this orbital angular momentum, as anti-parallel in the anti-parallel manner, this will give you, both will have same energy, and we represented it by this. So this is a doubly degenerate ground state, and this is a low-lying energy excited state, which is also degenerate when the spins are spin angular momentum and the orbital angular momentum both are parallel to each other. So there are two ways, up spin, down spin, and accordingly parallel angular momentum due to orbital motion parallel angular momentum due to orbital. So these are two ways in which this state can be arranged. So at very low temperature you will find that the degeneracy is 2, and at slightly higher temperature the degeneracy overall you will have both, all these states will be populated, and your partition function will be can have maximum value of 4 at slightly higher temperature. And so this is the kind of so we have a doubly degenerate ground electronic level of NO with the spin and orbital angular momenta around the axis in opposite directions, this, and a doubly degenerate first excited level with the spin and orbital momentum parallel, as in this case. The upper level is thermally accessible at room temperature. So this is, the gap is less, and simply keeping the molecule at room temperature will excite it from the ground state to the excited state, because the kT, the value of k into T is much higher as compared to the this energy gap. So both the energy levels will be populated, and the partition function will be greater than 1. In all other cases, in most of the molecules, you have the at room temperature the electronic partition function is equal to 1. So and because this is a special case that we are discussing, where the ground state is degenerate, the separation between energy levels is so low that it can the higher electronic state can be accessed at the room temperature. So we have slightly greater energy one, the upper one that we have discussed, and lower one which is denoted by this. So 2 pi 3 by 2 and 2 pi half term as denoted here. So this is the multiplicity, this is the angular momentum that we are talking about, 3 by 2. The separation with which arises from spin orbit coupling is only 121 cm inverse. So this, at normal temperature all 4 states are thermally accessible. So if we so E half is 0, and this is the 2 levels of we have 2 energy levels, and we level them as this one. So first one, we ground state we have to take it as 0, and then we assign E3 by 2 is epsilon. The partition function can be written as degeneracy into the e to exponential term, e to the power minus beta epsilon j, which further, if you as you are taking the summation, initially both the ground state degenerate, so this is you will get this value as 2 plus 2 into epsilon to the power this. So if you plot the function, you will find initially it starts with 2, in contrast to all others where it will start with 1. In all other molecules which have larger molecules, basically you will have this will be starting at 1 in all other cases, but in this NO molecule you have, because of the degeneracy of the ground state, when temperature is low, this is the partition function is equal to 2. As you increase the temperature, it gradually increases. At very high temperatures, when you achieve room temperature, suppose this all the this excited state is also populated, first excited state. So the partition function is now 4. All the 4 states are accessible. So this is the variation that we have. So that's what we talk about, that this curve resembles a 2-level system. So first level here, and then it rises exponentially and achieves plateau-like situation. Graph is obtained over here. Okay, so this is maximum value that is approachable is 4. So that's all about the partition function, and all these components will contribute to the energy, the overall partition function of a molecule. This, so you have electronic energy levels, you have vibrational energy. So partition function corresponding to electronic energy, electronic partition function, then vibrational partition function, rotational partition function, and the translational partition function. So all these taken together will be able to describe the energy of a system in a bulk phase. So that's the importance of this partition function is when you have a large number of molecules in a container, you can describe the overall energy by connecting by understanding the individual molecules and then connect it together, use a summation integration and reach to the final expression of a bulk property in a so that's what I highlighted in the previous class also, that it is acting as a bridge and help you trace out the entire how the property has evolved starting from an atom to a large number of molecules which are normally there in a container or in a crystal that you analyze, that you use for your any application. So that's all for this class. Goodbye.